Hey guys, in this video we are going to balance a redox reaction under basic conditions. So in this problem we're given a reaction and of course tasked with the goal of balancing this guy. Now remember, with redox reactions the balancing process is much more complicated than what we're used to with other forms of chemical reaction equations. With our old method of balancing, all we had to do is simply go through the chemical reaction and basically look at how much of each atom type show up on the reactant side and the product side, introduce stoichiometric coefficients to ensure that the same number of each atom type are showing up on the left and right. With redox reactions, we've got a different problem. In addition to balancing the number of each type of atom on either side of the equation, we also have to take into account that there's charge. There's actually a movement of charge. By definition, a redox process is a process in which electrons, charged particles, are actually moving between reactants. So what I'm going to do is introduce one of many methods for balancing redox reactions, which is the method of so-called half reactions. So in this method, we're going to break this down to essentially a 5-step process. And following these steps, essentially following this recipe, is guaranteed to get you to the correct answer. So I ask that you bear with me. It's a little bit time consuming, but learning this pathway through and through will get you the right answer every time. So when you're met with a chemical reaction equation, such as this, a couple red flags should go off. You're told to balance this guy, but you notice right off the bat here that we're pretty far off, okay? And in order to go through and basically recognize, let's say you weren't told it was a redox reaction, in order to recognize this as being a redox reaction, you should immediately think of oxidation numbers and look at oxidation numbers for each one of the different atom types and see if they're changing, okay? Now in this problem, there's no guesswork there. We know that they will be changing. But if we're going to write out half reactions, our first step is going to be to still write out each one of those oxidation numbers so we can see which reactant is being oxidized and which reactant is being reduced. So basically, we're going to go through each one of these reactants first and assign oxidation numbers. Our first reactant here, NO2-. The oxidation number for oxygen in this case is going to be -2. And notice that we have 2 oxygens, so that's going to give us a total of a -4 here from all the oxygen atoms contribution. And that -4 added to the oxidation number for nitrogen had better give us that charge of -1. So the only way that we can essentially make that happy is by adding an oxidation number of +3 to the nitrogen. So again, you can do a little mental check on each one of these, which I encourage you to do as we move through. Add up the sum total of all the oxidation numbers, make sure it equals that overall charge. So doing the same thing over here. Oxygen again is going to take a -2, and now we have 4 of them, so that's a -8, and we need to add something to -8 to get us to -1, which of course is going to be 7. Over here we got a -2 again. -2 times 3 is going to be -6. We need to add something to -6 to get a -1, which is going to be +5. And same sort of thing over here at the end. Now, let's look at what's going on. We very clearly are seeing oxidation numbers changing. So the first change that we can recognize is that this nitrogen is going from +3 to +5. So if my oxidation number is becoming more positive, then what's happening, right? So remember, it's electrons are the charged particles that are being transferred here. So if I'm going from something that's +3 to +5, it's becoming more positive. And so if something's becoming more positive, then that means it's losing electrons. And remember our acronym, the oil rig. So if we're losing electrons, we know, according to oil rig, oxidation is lost, right? So that means that this first NO2- species is in fact being oxidized. Now, if we come over here and we look at our manganese, okay, the manganese in this case, we are now changing from a +7 over here to a +4. Can move that over a little bit. Okay, so now if we're going from +7 to +4, what's happening now? Well, now we're becoming less positive. And again, if it's electrons that are moving around, going from a +7 to a +4 requires the addition of electrons. So you're adding electrons. Again, according to oil rig, reduction is gain. We now have the reduction half reaction. Okay? So doing this little analysis allows us to write down two reactions, which I'll abbreviate oxidation and reduction here. And I'm now going to split apart these terms. So I'm going to give myself a little bit more room here. The first one, NO2 minus half reaction. It's forming NO3 minus aqueous, right? And then the reduction portion has an MnO4 minus aqueous going to my MnO2 solid. Okay, so that's our first step then. Assign oxidation numbers. Then we are going to form half reactions according to which compounds being oxidized and which compounds being reduced. Okay, now looking at each one of these half reactions, we are now going to separately carry out a bunch of balancing steps. Now, the first step that we're going to take out in balancing the half reactions is actually balancing the half reactions with respect to atom type first. Remember, we're ultimately going to have to balance both atom type and charge. But first, we're going to essentially forget about charge, balance with respect to atom type first, then come back in our next step and look at charge. So, balancing with respect to atom type in this reaction, a problem comes up. Obviously, nitrogen is balanced in this case, but oxygen is very clearly not. 2 oxygen atoms on the left, 3 on the right. So, going back to previous examples, before we talked about redox chemistry, what you're used to doing is just introducing stoichiometric coefficients and making everything nice and pretty. Equal number on the left and right, no problem. Is there any stoichiometric coefficient that we can put in front of these two guys and get a balanced chemical reaction equation? Well, the answer is no. And the answer is no here because you've always, for every unit of NO2 you have, you've got 2 oxygens. For every unit of NO3 minus you've got 3 oxygens. So what we end up doing is actually following a special protocol for balancing with respect to atom type. Right? So the protocol is as follows. The first thing you look at is all atoms that are not oxygen or hydrogen. Anything else but oxygen and hydrogen. In this case, that's nitrogen. Nitrogen's the only guy that we care about, and we're going to look at those non-oxygen hydrogens and balance with respect to that atom type. In this case, our work is already done. Nitrogen, there's 1 nitrogen, we're good. So now, after balancing all non-hydrogen and non-oxygen atoms, then we go in and we balance oxygen first. So again, we're putting hydrogen off to the very end. We're going to balance oxygen first. Now, we're going to balance oxygen by adding in water molecules as needed. So water molecules, of course, H2O, each one of them provides a single oxygen atom. So if I've got 3 oxygen atoms on the right, I'm going to need an additional oxygen atom on the left. So I'm going to put in an H2O over here. Once I put in that H2O, now I've got a total of 3 oxygen atoms on the left, and I'm happy. We have now balanced with respect to both our non-oxygen hydrogen, nitrogen in this case, as well as our oxygen atoms. Then, our next step is to balance with respect to hydrogen atoms. You can notice here that when we are balancing with respect to hydrogen, we have 2 hydrogen atoms on the left, and we don't even have a hydrogen-containing species on the right, so there's 0. Okay? So for this step, what you do is you add in H+ ions, protons, as needed in order to balance out hydrogens. So we've got 2 on the left, so we're going to have to balance this out by putting 2 H+ species there, protons, on the right-hand side. Okay? So now a quick analysis of this chemical reaction here, this half reaction, will tell us that, in fact, we are balanced with respect to hydrogen, oxygen, and nitrogen. If we were under acidic conditions, we'd be done and we'd be ready to move on to the next half reaction here. However, because we were told in the problem that we are under basic conditions, what we now need to do is a final step where we add in hydroxide ions, and we add enough of them to completely neutralize all of the H+ that we previously added. So if I added 2 H+ molecules here, that means I need to add in 2 OH- molecules. Now, I already had a balanced chemical reaction equation. So if I add something to the right, what do I need to do? Well, I'm going to have to add the same thing right over here. Okay? And so I'm going to rewrite this guy because we're going to keep him around for a while. So my first half reaction is now going to contain 2 OH- plus H2O plus NO2-, and that will be forming my NO3-, plus, now what happened here? I've got 2 H+ plus 2 OH-, that's going to give me 2 water molecules. So I'm going to have 2 H2O. Okay? Now if you're looking at this, you'll notice that, well, hey, after I formed 2 H2Os on the right, okay, I had 1 H2O on the left, so 1 on the left cancels out 1 of the H2Os on the right, so I'm going to come back to a final balanced half reaction, balanced with respect to atom type, that looks as follows. NO3-, let's not forget our subscripts here, and we have just a single H2O, right like this. Okay, so it's getting a little crowded there, so let's clean this guy off. All right, so in that way, we now, once again, have a balanced half reaction, balanced with respect to atom type, okay? And we're going to leave it there. We'll come back to charge out in a second. First, we have to come down here to our reduction half reaction and perform the same operation. So with our reduction half reaction, what we have is essentially the same protocol that we're going to follow. We're going to look at all atoms that aren't oxygen or hydrogen. In that case, it's just manganese, Mn. There's 1 Mn on the left, 1 on the right, so we're done there. Just as in the previous problem, we don't have any extra work to do there. So we're going to leave it as is. Then we're going to come in, we're going to say, okay, well, what do I need to do to balance oxygen? We've got 4 on the left, 2 on the right, so I'm going to add in 2 H2O molecules to give me a total of 2 oxygens, 4 oxygens on the right, 4 oxygens on the left. Then I'm going to come back in and I'm going to once again add in protons in order to balance out my hydrogens. I added 4. So that means I'm going to have to add 4 H+ to the left-hand side. Okay? Now, if I was under acidic conditions, I'd be done, but because, once again, we're under basic conditions, we are now going to add in hydroxide ions in sufficient number to essentially neutralize all those protons. So doing so is going to give us the following equation. We're going to have an H+, and then we're going to add in 4 OH- ions. Okay? And these problems are quite lengthy. I recognize that. And now if I added in the 4 OH- to the left to neutralize this, then I need to do the same thing to the right. 4 OH- over here. And then we'll do the same thing that we did on the previous problem. We're basically going to simplify this half reaction. We're going to simplify this half reaction by combining terms. In this case, we're going to have 4 water molecules forming here on the left, and we've got 2 over here on the right. So we're going to have a net of 2 water molecules left over here on the left, plus our MnO4-, and that's going to be forming the magnesium oxide. And remember, we canceled out these water molecules, so they're not even there anymore. We just have our 4 OH minus hydroxides. Okay, so that completes our third step. Okay, our third step of balancing each half reaction with respect to atom type has been accomplished, and now we're ready to go back and look at charge. Okay, so with charge, and the charge, basically it's the same concept as atom type. You must have the same number of each atom type on each side. Well, according to balancing with respect to charge, right, and thinking about charge, essentially demands that we have the same total charge on the reactant side as we have on the product side. You can't create or destroy charge. All right, so to add up charge, we need to be a little careful and we need to do some bookkeeping here. So I'm going to introduce charges in green, not to be confused with the oxidation numbers that I have up here in pink. Okay, so the total charge contribution from this term right here, I'll draw this guy right up on top. The total charge for two OH minuses is going to be a total of 2. Because each OH minus gives us a -1, and there's 2 of them, so we're going to have a total charge of -2. Okay? Then we're going to come over here, and we're going to look at this guy, right? NO2 minus, right? Each NO2 minus gives us a -1 charge, and according to my stoichiometric coefficients, there's only 1 of them, so we're going to have a total charge of -1. Okay? This term right here is going to give us, again, total charge of -1. And water is neutral. It's not going to be contributing at all. Okay? So what's happening here, the problem we need to solve is we need to figure out how can we add in charges so that the sum total of all the charges on the left is equal to the sum total of all the charges on the right. So obviously, -3 is not equal to -1. So we're going to need to do something. We're going to need to put some charges in there. Now, there's only a certain type of charge that we can add in working through these problems. And remember, redox chemistry involves the movement or transfer of electrons. So electrons are those charged particles that we are going to be adding into this problem. Now remember, electrons, by their very nature, have a negative charge. So we need to balance this little charge expression here with the only option of adding in negatively charged electrons. So if I've got a total of -3 over here and only -1 here, the only way I can get these expressions to balance is if I somehow add in another -2 over here on the right-hand side. Okay? And so -2, well, that corresponds to adding in 2 electrons. Okay? Now, I'm going to do the same thing down here. We'll do a little math below. Okay? Water is neutral. Manganese, -1. 0 plus -1 had better be equal to, this manganese guy is going to be 0. And hydroxide, now there's 4 of them, so it's going to be a -4. Okay? So now we ask the question, how can I add in negative charges to make this equality hold? Well, -1, -4. I somehow need to add an additional -3 to the left-hand side. Well, -3 is going to come about by adding 3 electrons over here. Okay? And you can always do a quick sanity check here and double check that the way you've added electrons, not only is it balancing charge, but is it in line with how we defined each one of these half reactions, namely as either an oxidation or reduction process. Well, remember, oxidation is loss of electrons. So if an oxidation process is occurring, electrons are being lost or given off, so they better be showing up over on the product side, which they are. Okay? Similarly, a reduction process requires electrons to be essentially taken in as a reactants, and that is in fact what we see down here. So, giving ourselves a little bit more room here, we can move that out. So we've got our 3 electrons. Okay. Now, our reduction reaction here and our oxidation reaction here, of course, aren't occurring in isolation. So finishing our 4th step here, balancing charges, isn't the end of the story. We need a final step. And this final step comes down to basically thinking about what do I have to do to each one of these half reactions to make them play nicely with each other. What do I mean by that? Well, this oxidation process of giving off electrons is intimately coupled with the reduction process of gaining electrons, which means every electron that's given off up here must come in down here on the reduction side. So this number of electrons had better match this number of electrons. As you can see in this problem, it does not. So what do we have to do? Well, what you're going to do, remember, you don't want to just arbitrarily change that to a 3 because that would destroy our charge balance. Okay? And you can't arbitrarily change anything else and leave everything else the same because it would unbalance the total number of atom types on each side. So what we have to do is multiply the entire half reactions by a certain value, and we're going to choose that value so that the number of electrons in both half reactions matches. So you're basically looking for the least common multiple. In this case, we've got 2 and 3. The least common multiple will be 6. So if I want to get this up to 6 electrons, what I'm going to do is come through here and I'm going to multiply everything by 3. So my 2 is going to become a 6. This becomes a 3, this becomes a 3, this becomes a 3, and I then have my 6 electrons out here. Okay, so I've got my 6 electrons. Now I'm going to come down here and I'm going to multiply everything by 2. That's going to become a 4, 2, 2, and 8. Okay, now once I have electrons balanced, I can carry out the very final step, which is to basically add both of the half reactions back together. And at this step, the number of electrons, by how we've set up the problem, had better cancel out. Of course, 6 on the left, 6 on the right, 6 on the left. Those guys are going to be gone. And then we're basically going to go through term by term and write out all the surviving reactants and products, and we'll arrive at our final answer. So 6 OH minus on the left, 8 on the right. So we are going to have a total of, that 6 is going to go away, and this 8 is going to go down to a 2. So we're going to have just a single product over here of 2 OH minus, okay? Looking at the NO2 minus, we see that, well, there's no NO2 minus on the right-hand side, so we're just going to keep him as is. 3 NO2 minus, okay? So we've used him, right? Then we'll come over here to the next reactant, okay? Our next reactant is 4H2O. Do we have any H2O on the other side? We do. Right? We've got 3 H2O here, so that's going to cancel out the 4. We'll just have 1 left over, so we're going to have H2O liquid, right? And then our final reactant is then going to be our 2MnO4. Okay? Now coming over to the products, we have our 3NO3 minus aqueous. We've already used up all that water, took care of that in the previous step. We've already written down our OH minus, and so our final reactant is then going to be MnO2 solid. And you can then double check this and make sure that you have everything balanced with respect to atom type and charge. And then you can essentially come back up here and say, okay, well, what are my coefficients? So my coefficients for NO2 minus is going to be 3. For MnO4 minus, which we forgot the minus sign right there, we have a 2. For NO3 minus, we've got a 3. And then last, we have our final coefficient. And that is how you balance a redox reaction under basic conditions.